Previously, we talked about K-means algorithm as a clustering algorithm, and in K-means algorithm, we had two different steps. Right? So we had a assignment step and we had an update step. In the assignment step, we actually assigned all the samples into one of clusters exclusively. Okay, and then in the update step, we actually updated the mean of each cluster. Okay, so now we're going to talk about mixture of Gaussian. And mixture of Gaussian can be used to estimate a distribution when the distribution is kind of complicated. And at the same time, we can use mixture of Gaussian for clustering too. So before talking about clustering, let's talk about the mixture of Gaussian as density estimation. Okay, so a distribution can be approximated by a weighted sum of m component Gaussian densities with parameters like this. Okay, in the previous chapters, we actually talked about a maximum likelihood estimate for a single Gaussian distribution. Okay, so in that case, we assume that all the data samples can be approximately modeled by a one single Gaussian distribution. But sometimes when we have some data samples like this in the in one-dimensional space, okay, then we have a lot of samples here and here, and the Gaussian distribution is not a perfect model. Single Gaussian is not perfect. So in this case, probably the distribution should look like this. Okay, and this distribution is a little complicated than simple probability distributions. So instead of using more complicated equations, we are going to use two Gaussian distributions, okay, merged, combined. So it is a mixture of Gaussians. Basically, we have one Gaussian here and another Gaussian here, and these two Gaussians should be combined based on the weighted sum. So probability of x given parameters. Okay, this is actually likelihood. Okay, this probability can be modeled by weighted sum of these Gaussian distributions. Before, when we talked about probability with single Gaussian distributions, x theta was something like this, right? So when we assume that the data sample can be modeled by single Gaussian distributions, then this p, the probability of x given theta, can be modeled by this. And in this case, we have two parameters, mu and sigma. And mu and sigma can be estimated based on the maximum likelihood estimator. So we have derived these estimators. So now, in this case, instead of using just one Gaussian distributions, we have multiple Gaussian distributions. And these Gaussian distributions are combined with different weight. So we have one nice figure here. When we have some samples like this, then we need three Gaussian distributions. Okay, then the first Gaussian distribution is in charge of taking care of these samples, and this one should model these samples, and this one should model this one. Okay, so basically we have three Gaussian distributions with different mean and sigmas, and mean and sigmas, and mean and sigma. But that's not it. Okay, so we have some samples here and here and here, and sometimes we have 10 samples here and we have 1,000 samples here. Then we can model a Gaussian, we can learn the Gaussian distribution with 10 samples or 1,000 samples, but they have different kind of weight. So if we have 10,000 samples, then this Gaussian should have more weight. That is actually a pi. Okay, so depending on how many samples are in that component. So if this Gaussian is explaining a lot of samples, modeling a lot of samples, then this one will have a high weight. Okay, and if this one has a few samples, then this one will have a small weight. So depending on how many samples are here and here and here, and we assign this pi, and by weighted sum we can have this nice distribution. That is actually our p of x given theta. And by the way, theta includes all the parameters, including pi sub I and mu sub I and sigma sub I. Okay. And again, in this case, even in this case, we have to define the number of components in advance. Okay. So as we did in the k-means algorithms. In k-means algorithm, we defined k first, and then we actually get the clusters. Likewise, in this case, we define m, the number of components. And pi sub I is probability of I, probability of the component. Okay, so this one is 1, and this one is 2, and this one is 3. So we have 3 components, and the prior probability can be actually approximated by the number of samples, roughly speaking. So we'll see the exact equation later. Okay, and then this Gaussian distribution is actually p of x given I, which means given I means when we choose one component, and then what is the likelihood. So when we have a sample here, around here, then if we choose 2, okay, when I is 2, then what is the likelihood? How likely this distribution is generating this point? Quite small, but still there is probability here. It's not 0, okay? And this guy, p of x given 3, is quite high, okay? So in this case, this point can be can belong to the third component, but at the same time, this one can belong to the second component, but with a different probability. Okay, so now this is a little different from k-means, right? In the k-means, one sample can be categorized into one cluster exclusively, but in this case, we have soft assignment. Okay, so anyway, for now, in this slide, important thing is that the mix of Gaussian can model a little more complicated distribution with multiple Gaussian distributions. Okay. Okay, now let's think about this mix of Gaussian in detail. Okay, so in the mix of Gaussian or Gaussian mixer model, basically GMM and mix of Gaussian, they mean the same thing. Sometimes we use MOG, sometimes we call it GMM, okay? They exactly same thing. And in MOG, we have latent variables. Okay, so we're going to talk about what is the latent variable, and then this latent variable is important in expectation maximizations. Okay, so given this mix of Gaussian distribution, and to estimate parameters, we have to know which component x belongs to. Okay, so think about k-means algorithm. In k-means, we have 2 steps. First, we have assignment step, and second, we have update step. In the update step, we actually used mean. We didn't talk much about variance, right? It means in k-means algorithms, we assume that we assume that each cluster makes a Gaussian distribution with the same covariance matrix, isotropic covariance matrix. Okay. So in that case, we actually used just the mean of clusters. And in the assignment step, this assignment is exclusive, hard decisions. Okay. So one sample belongs to one cluster. So if we actually assign the samples to clusters first, and then in the update step, we consider this assignment fixed. Okay, so we know the assignment and we know which one belongs to which. Now we update the mean, which means we update the parameters. So likewise, we have to know where this one belongs. Okay, so let hidden variable g sub I indicate if x belongs to component I. Okay, so we introduce a new a variable z sub I. Okay, and if x belongs to component I for sure, then g sub I is 1. Okay, and then in other words, z is an m-dimensional binary random variable, something like this. And the sum of all the elements should be 1, which means x belongs to one component. Okay, so with this example, x belongs to second clusters. But we don't know this one. So if we know x belongs to the second cluster for sure, then z is like this. Okay, so z is a hidden variable which is not given. We don't have this knowledge yet. Okay, and if we know this z sub ni of xn for all n, which means for all the samples we know where this one belongs. Okay, so which component this one belongs to, we know that. If we know that, then estimate is simple, which means in the k-means algorithms, once we assign all the samples into one of clusters, then estimating, so in k-means algorithm we just estimated this mu, right? So in k-means algorithm we estimated mu sub I. Okay, likewise in the mix-up Gaussian, if we know which component xn belongs to, okay, if we have this kind of knowledge, this point belongs to the first cluster, this one belongs to the second one, and this one belongs to the third one. If we know this kind of knowledge, if we have this kind of knowledge, then estimating these parameters are not that hard. So pi sub I can be based on the number of samples, and mu sub I can be just the mean of sample average of these samples in the cluster, because we have this knowledge. Okay, again, if we know which component xn belongs to, which means we have this one. Okay, if we know this variable, then estimating this one is simple, like this one. So we have red dots and green dots and blue dots, and the red dots belong to the first cluster and green dots belong to the second cluster, etc. Then the mean of the first cluster is simple, and the mean of second cluster is simple, and mean of the third cluster is simple, and the variance is 2. Okay, and pi sub I is simple. We can just count the number of samples. Okay, so if this is the case, then life is easy, but it is not the case in most cases. In most cases, we have samples in this way. So we don't know, we have no idea about this one. we don't know which component xn belongs to. For example, if we have one point here, is it belong to, does it belong to the first cluster or second cluster? We don't know. Okay, so even this one, is it in the third cluster? So it looks like, yes, we already checked this one, so it looks like, okay, so this one belongs to the third cluster to us. Okay, but when we actually calculate that, we don't know, we have no idea. Okay, so the problem is quite complicated. We have just a bunch of samples, and we can guess like the samples are, some samples belong to one cluster and the other some other samples belong to other clusters. So maybe there will be a couple of clusters, but we don't know. We have no idea about what kind of share and what kind of relationship between the clusters and samples. We have no idea. Okay, but just basically we assume that these clusters can be approximately modeled by a Gaussian, and we can use a mix of Gaussian to model these samples. That's the starting point. Now let's talk about expectation maximization, or EM algorithm. Okay. So again, let's compare it to two different cases. First case has just one Gaussian. Okay, so we have simple distribution. Given data samples, we want to assume that these samples are from one Gaussian distribution. And in that case, we know how to estimate the parameters. We know how to estimate the mean and variance. We can use maximum likelihood estimator. Okay, so in the maximum likelihood estimator, the mean is the estimator of mean is just a sample average, and the variance estimator can be calculated a little, is kind of a sample variance. Okay, so single Gaussian is easy, but now we have a mixture of Gaussian. Then the learning mixture of Gaussian is a little harder than the simple case, because in the mix of Gaussians, we don't know which component one sample belongs to. We have no idea about that kind of assignment. Okay, so before modeling the distributions that we don't know, right? So if we don't know this assignment, then we cannot update the parameter. So as we did in the k-means, then we're gonna do this iterative approach. So basically, we will update the assignment. We reassign, and then we update the parameter. And based on the parameters, then we will reassign. Okay, so we have assignment step and update step, basically. Okay, but in this assignment and update steps have different names, because when we derive the equations, okay, so we have expectation step and the maximization step. Okay, so that's why we call it EM algorithm, expectation maximization algorithm. But basically, this EM algorithm is quite similar to k-means algorithm. Okay, more generalized version of k-means algorithm. And as I said, it is an iterative optimization method to estimate parameters. Parameters include pi I and mu I and sigma I, and given measurements x and data samples when there are hidden variables z. Hidden or nuisance variables z. Okay, because z is a troublemaker. And it can maximize the posterior probability. The EM algorithm can maximize the posterior probability or likelihood. So expectation maximization is a general algorithm. So if we have a posterior probability to maximize, then we can apply EM algorithm. Or if we have a likelihood, then EM algorithm can maximize the likelihood. Okay, so if we have a likelihood, then EM algorithm is a generalized version of maximum likelihood estimator. Okay, and to optimize the posterior or likelihood, a naive approach would be an alternative optimization between theta and z. That's what we did in K-means algorithm, right? So we actually assigned z and then we updated parameters. Again, in the K-means algorithms, we had only one parameter, mu sub I, okay? And we didn't care much about the variance. So it's quite a simple model. And in EM algorithm, however, instead of using the best z, it uses the distribution of z. Okay, so this is quite important concept. So we can find the best z, and we can update the parameters based on best z. But this is not perfect. Instead, we can use the distribution of z. Like, let's say z is, we have 3 clusters and we have 1 0 0. This is an assignment of one sample. Okay, so for one sample, z can be three-dimensional vector binary representations. Okay, so 1 0 0, so it means this sample belongs to the first component. Okay, for sure. But how about this one? Yeah, this one belongs to the first component pretty much, but still, this one belongs to the second cluster a little bit, right? But how about this one? This one belongs to the first cluster and second cluster half and half. Then can we use 1 0 0 or 0 1 0? Okay, which one is correct one? Both, right? But both are correct, but not exclusively. So they are correct with the same probability. So this one 0.5%, okay, 50%, and this one 50%. This one is correct 50 times, and this one is correct 50 times. So instead of using the best one, so think about this point. For sure, the first component is the best choice, but second component has something to do with these samples, with some probability. So instead of using the best shot, we use the distribution of z. Okay, how likely this one belongs to this component? So we use this distribution. So which means we don't actually ignore all the information. We use all the information. We don't ignore any tiny little informations. Okay, so there's the difference between MAP and MLE and Bayesians. Okay, so MAP and MLE, we actually use the best estimator. So it is point estimator. So we find the best parameter. Okay, but in Bayesian approach, instead of using the best parameter, then we use the distributional parameter. So in Bayesian, actually P of x can be P of x given theta, P of theta, d theta, right? So actually this one is P of x theta. So this one is marginalization. So with the different probability, actually, we select theta, and then given this theta, we model the probability of x. Okay, so we don't pick the best theta. So instead of using P of x given best theta, instead of using this one, we actually use this one. Okay, this one is more correct than this one. Okay, this one is based on one point, one best shot, but in this case, we actually integrate all the possible thetas with a different probability. Okay, so we have to compare this one and this one. In this case, theta has different probability. Okay, so this one is connected to this one, so distribution of z. So in this case we use theta, but this one means we use z here, something like that. Okay,